can get started.
Okay. It's got it, and then you. Okay, excellent. So let's get started. So I'm so happy to be here. First of all, thanks so much for the invitation. So today we're gonna talk about consistent diffusion models and learning from corrupted data with ambient diffusion. These are two recent works of mine. They're gonna be presented on NeurIPS 2023. And without further ado, let's get started. So a lot of like a great part of this talk is going to be about like generative models and a little bit of history. So generative models are not new. They have been around for a while, but they didn't actually receive that much attention in the past. And that was for a good reason. So they used to be generating like things like this. So if you were a researcher back in like 2016, you could get your paper published at ICLR for generating like high realistic human faces. That was considered like high realistic back in the day. But you know, if you're trying to submit your paper to any venue today, you wouldn't probably get away with this. And the reason is that like generative models have actually gone like a long way since then. And today's generative models are actually like pretty amazing. So I wanna start with this statement. They're actually like mind-blowing. So even like since like 2020, we have like StyleGAN, that is like a neural network that can generate like very high realistic images of human faces. And there is literally a website called This Person Does Not Exist, that every time you go there, you can like refresh and you get a new person that does not exist. You refresh another time, you get another person that does not exist. And you know, we're not just like constrained with generating faces. We can like we actually do have generative models for different modalities. So we have generative models that can generate proteins that have never been encountered in nature before. So you can do like de novo protein design with proteins, and these proteins actually fold, and we can have them in the lab. And also like generative models can like follow prompts from the user. So the user can go and say like, oh, I want like an astronaut riding a horse, and the generative model is gonna generate an image like that. And I'm pretty sure there are like no astronauts riding horses in the space station, so we can like safely assume that like this generation was not in the training set. So generative models have actually like become really, really good. So the real question is like, what can we do with these models? And that's what I wanna like partially answer in this talk. And a bunch of ideas. Like one thing that we can do is we can generate fake photos for our social media profiles. You can go like create fake photos of yourself, but like some would argue that this is actually like a bad idea. Maybe you should do, maybe you should not. You can like create art. There are like generative AI artists. That's like a better idea. But like one thing that we want to do is we want to use generative models as priors to solve real like scientific problems. We will be calling these problems inverse problems. So let's first like talk about what are inverse problems and why are they important. So inverse problems are like problems in which we are trying to reconstruct the signal X, but we do not get to observe X directly because there is some devilish adversary that is going to hide our signal X and give us some measurements Y. So this is like the setup. And like what recover means is like open to interpretation. We might be interested in like maximizing the likelihood of X given Y. There's some probabilistic model that like connects X and Y, and we might be interested in find like the most likely X. Or we might be interested in like to taking like a softer approach. So we want to sample from the conditional distribution of X given Y. So there are a bunch of like famous inverse problems that can be posed in this framework. So this is like an image of my academic advisor, Alex Timakis on the right. This is like our signal X star. And then some devilish adversary created this image that like half of Alex's face is missing. So this is the famous problem of in-painting. And there are other famous problems like denoising. So you have like some noisy version of Alex, or the version of image that you have is like blurred Alex, or you have like compressed sensing where you observe like Gaussian measurements of the image that you want to reconstruct. So these are like a lot of like famous inverse problems. And one thing that they share in common is that they're linear. So there's like a linear model, y equals ax plus some noise, some Gaussian noise. And all of these like problems, the in-painting problem, the denoising problem, the deblurring, and the compressed sensing, they can be posed as like specific cases. For different matrices A, you get different like inverse problems. And like you would say, like, why do I care about this? You know, like it's not common that someone gives you like half of Alex's face and then you want to reconstruct it. It is actually true that in nature, these problems arise like in multiple scenarios. So inverse problems have applications from MRI acceleration to protein engineering. For example, for protein engineering, what you do is you have some protein that you care about, and you want to make it like a little bit different for a certain reason. You want to make it like more thermostable. So you can inpaint part of the protein and ask the generative model to complete the missing part. And maybe you end up with different proteins that have like desirable proteins or desirable characteristics. Or even in black holes, because in a black hole, you cannot definitely get to observe like the whole image of a black hole. You know, light cannot escape the gravitational forces. So you only get to observe some measurements. So there are like a bunch of scientific applications. And inverse problems are actually important. And the traditional way to go to solve this problem is actually like the following. You have like some data set of clean images on the right here. And what you do is maybe you want to solve the inverse problems of deblurring. So what you do is you get the clean images, you blur them, and you train a neural network that takes as input the corrupted image, the measurement Y, and it's trying to predict the clean image. So you have a bunch of those. You train your neural network with like a loss, maybe it's the mean squared error loss. And then at the end of the day, you have your deblur. So that's like one way, the traditional way to solve inverse problems. So there is a problem with this way, and the problem arises from the fact that inverse problems are usually ill-posed. So what does that mean? It means that there are like a bunch of like clean images that could have generated your measurement. So if you're optimizing for this loss, you're going to have this issue, the regression to the mean issue. What does that mean? It means that like if there are a bunch of clean images that could have generated your measurement, and you train like your neural network to go to one of them, what is the neural network going to learn? It's going to be giving you the expected value of the potential candidates. But if you take like some weighted average of good solutions, you're not guaranteed to have a good solution. What you're actually going to have is you're going to have like a blurry reconstruction. And a very good example of that is like the colorization inverse problem. So here you have like a grayscale image of a dog that is like in the grass somewhere. And you like the problem that you're interested in solving is you want to like colorize it. And you know, you have no idea like what the dog looks like. Maybe it's a brown dog, maybe it's like a black dog, maybe it's a white dog. And what you're gonna find if you train this model is you're gonna find a green dog. But it's pretty clear that there are no green dogs, or at least not ones that I'm like aware of. So this is actually like a very interesting case of this regression to the mean problem. So instead of doing like this classic approach of like we have an inverse problem, we create a data set, and then we just optimize for that, we are interested in taking like a different approach through generative models. So here's like the setup that I have been working for the last 4 years in my PhD. And it goes like this. There are some training data from some distribution of interest. And then you train a generative model on this distribution. So what is this generative model doing? It's basically learning to be creating like fake dogs or fake faces. And that's not useful at all. But what is useful is you want to use this model as a prior to solve these inverse problems. So you want to like basically use this generative model to imagine a potential completion to your missing pixels, let's say. And if you are like interested in solving this problem, you have to be looking at all the different stages of the pipeline, from the training data, the generative model to the inverse problems. So we have a lot of work on that. Like early in my PhD, we're like trying to create like more efficient generative models. Then we look at the training data because we want to scale these generative models to billions of text and image data sets. And then you want to be looking at like, oh, what happens when you scale these models? Maybe there are like emerging phenomena happening, and then you want to look at them. And also like a very important thing is like, how is your training going to look like? What is the class of the generative model? How are you going to train it? What's the training algorithm? And you have work on that. And then finally, once you have this box, how can you use it as a prior to solving those problems? And depending on like what the generative model looks like, maybe it's a GAN, maybe it's a diffusion model, there are different algorithms. And for these algorithms, you might be interested in like analyzing the theoretical performance or even applying them in scientific applications. For example, we have applied this to MRI. So that's kind
Giannis,
of like yes.
Can I ask a question?
Yes.
So like when you're optimizing for this, like what's the loss? Is it just like pixel reconstruction, like a mean squared error between the pixel of your target and your output, or what do you use?
There are different metrics to check how well your model performs in image reconstruction. One of them is just like mean squared error. Another could be like you can have like a perceptual loss function like LPIPS.
Oh, okay.
You know, you have like a test set of images that you did not use during training, and then you wanna, you know, the ground truth, and you check how well you perform on the test set, and that gives you like a sense of how good you like your model is.
Oh, okay, cool.
Excellent. Okay, thanks so much for the question. So, okay, so this is like a lot of different things, and today we're not going to talk about all of them. We're actually going to be very conservative. We're just going to talk about how to train generative models that are actually good for inverse problems, and what are like what is the state of the art for like training generative models. So that's how the talk is going to go. The generative modeling approach, the benefit it has is that basically you need one generative model to solve only inverse problems. So no matter if you want to do in-painting or de-blurring or denoising, you can just use the prior to solve all these problems without retraining. And it avoids the regression to the mean problem that we saw earlier, because it's going to sample like one potential candidate over the many that could have generated your measurement, instead of just trying to find an average over all those. And we're going to come back to this point and see how it motivates today's generative models later in the talk. And finally, there are like extremely powerful generative models out there that you can like freely use, like stable diffusion, deep flow GForce, and so on. So there is like, this is actually the right moment to use these priors. Good. Okay, so moving on to the central part of this talk. If you care about what is the state of the art right now in generative modeling, this is all diffusion models. So diffusion models, there is something funny about them. And the funny part is that diffusion models are actually coming from supervised learning, that we just spent so much time like saying how bad it is, because it has all these issues of like regression to the mean and stuff. But they have a funny way of like solving this regression to the mean and turning this supervised learning problem into a generative modeling problem. So let's start with this. If you had like this noisy image of a cat and you wanted to basically denoise it, we could all agree that like a denoiser that is trained with supervised learning would probably do a very good job denoising this image. But what is, and you know, you train this generative model with a very simple supervised loss, as we said before. You create like the noisy version of the image, and then you're trying to predict the clean one. But what is generative modeling? Generative modeling is turning like boring randomness into interesting randomness. So you want to turn like just purely Gaussian noise into a phase of a person. And as we said before, this is going to fail. It's going to give you like this average phase because it doesn't really know what like human phase could have generated this noise. So just like doing this in one step, just having like this one-step predictor to turn like noise into data and training this supervised learning is not going to work because of this regression to the mean. But what we are going to do now is we're going to take an iterative approach. So I'm going to derive diffusion models from like just a very simple like algorithmic viewpoint. Because I want you to get an understanding of what this is actually doing in practice. And once we do this, I'm going to formalize and like show you why this is actually working. So here's what we're going to do. We're going to start from a very noisy image. Okay, we start from just pure noise. This has no information whatsoever about how the clean image looks like. And then we're going to ask our model to make a prediction of what do you think the clean image is. And because of all the things that I said to you, you're already going to tell me that this is not going to work. It's going to give us like an average image. But for a little bit, we're going to pretend that this image that we had in mind, like the one that the generative model had in mind, was actually the true image that generated my noise observation. And then what we're going to say is that we're going to say, oh, look, the noise image that I have was a clean image plus some appropriately scaled noise. And we're going to solve for the noise. So again, to repeat that part, you start from a noisy iterate. You ask the model, what do you think the clean image is? You have this prediction. You're saying, oh, maybe my noisy image was this clean image plus some noise. And then you solve for the noise. And then you can also say that, you know, at some point in history, my very noisy image was a little bit less noisy, and then I added a little bit of extra noise. And this noise we have already estimated. So we are going to solve for this new iterate, xt minus delta t, which is just a little bit less noisy image. And then we're going to repeat the process. So that's a lot to unpack. So let's put like a visual to understand what's going on. So we start with pure noise right here on the left. And then we ask the neural network, what do you think the clean image is? This initial prediction is pretty bad, but we're going to take a leap of faith and say that maybe it's good. And maybe that was the real image x0 that generated my noise observation. And then what is xt, the one that I am currently right now, is like x0 plus this noise. So we can estimate this noise. And then we can say that this xt was actually at some point an xt minus delta t plus this noise. And then we can just solve for xt minus delta t and move to a little bit less noisy iterate. And we repeat this process again and again and again. So at any point we are at the noisy image, we take a step to like predict what do we think the clean image is. we solve for the noise, and then we denoise a little. And then we denoise a little and a little and a little. And at the end of the day, hopefully, this is going to arrive at an image that looks like a normal cut and not like an average cut. So far, makes sense what's going on, how these models work. So this is literally how diffusion models operate. They do this recursive procedure. Okay, moving on. Great. Okay, so the update rule, the final update rule, I don't know if you can see it to the Zoom link, is basically saying that the new iterate is going to be my current iterate minus this term, appropriately scaled. Now, there is a very nice result from statistics that is basically telling you that this term that appears on the right, the one that we had in our update, is actually the gradient of a log likelihood. So this result is called Tweedy's formula. And Tweedy's formula is saying like a very nice thing. It's saying that the best denoiser, what is the best denoiser? It's the conditional expectation of x0 given xt, is basically the same thing as having access to the score function. What is the score function? The gradient of the log likelihood of the noisy distribution. So this is like a result that you can like easily prove from first principles. It's called Tweedy's formula. But the nice thing that Tweedy's formula allows us is it allows us to give a very nice interpretation of how diffusion models work in practice. Because diffusion models, what they actually do in practice, they're doing a step of gradient ascent to maximize the likelihood. So the way you actually moved in this algorithm is that you were in a noisy iterate xt, and you performed one step of gradient ascent to maximize the likelihood of the current noise distribution. Then you move to a new iterate xt minus delta t, and you repeated this process. The tricky part is that every time you do this gradient ascent step, your loss function is changing because the likelihood depends on the time t. So you start from the likelihood of a very noisy distribution, and as you move on and you move on, you steadily go to like distributions that are less and less noisy, and you're using their likelihood. So far, so good. Okay, so diffusion models are actually doing gradient ascent to maximize the likelihood, but this likelihood function is changing every time. Good stuff. So you might ask, like, okay, we derived this algorithm. Do we have any guarantees that this algorithm is going to sample from a right distribution? And the answer is yes, we actually do. This is coming from stochastic differential equations. I don't really want to go there. But what I want to say is that, there is this forward process. It's a stochastic differential equation. It involves like a drift term and some terms that adds noise. And there is a choice of functions f and g. And for that choice of function, you get the marginals of the corruption that we had before, which basically my noisy iter is a clean iter plus appropriately scaled noise. So the good thing about this stochastic process is that there are invertibles. So there is a different stochastic process that starts from noise and it moves all the way back to data. And this process, the only thing that you need to run it is you need to know the functions f and g. Those are fine. We already figured them out. And you also need to know the score. This reminds you of Tweedy's formula because the score is coming from the conditional expectation. And not only that, but there is also a deterministic process that does the same thing, and it has the same distributions. So if you run this process provably, you're going to sample from a right distribution. And it turns out that this process, the deterministic process, if you discretize it, you get exactly the update rule that we derived from this iterative algorithm. So at the end of the day, what diffusion models are doing is that having this very simple algorithm, you predict the clean image. Your prediction is bad. You use it to estimate the noise. You remove a little bit of noise and you repeat. And there is some like continuous tool that tells you that this algorithm is actually something from a right distribution. So that kind of like, the only thing that you need to run this is you need to have the gradient of the log like, which is called the score. And the score, you get it from conditional expectation through to this formula. And then for that, you use supervised learning. So that's pretty interesting because now we can just use supervised learning with this like funky iterative algorithm to basically create data from noise and to have a generative model. So we like somehow in the process, we sidestep this regression to the mean problem by just iteratively applying the same thing again and again. Cool stuff. So that's kind of like finishes the background section of diffusion models. So now let's talk about like what can go wrong. A small recap. If you lost me during that last part, now's your chance to come back to the talk. It's like here it has like all the points that you need to remember. So what are diffusion models? Diffusion models are generative models that they want to sample from some density P of X. And like the only thing that you need in order to be able to do that is you need to have access to this object called the score function, which is the gradient of the log likelihood. This log likelihood is changing based on time t. For like when t is really large, we talk about very noisy distributions. When t is low, we talk about clean distributions that don't have a lot of noise. But if you have access to this, to an oracle that estimates the gradient of the log likelihood, you basically can use it to sample from a distribution of interest. There is this nice tool called Tweedy's formula that tells you that the gradient of the log likelihood, or in other words, that score, is basically the same thing as the conditional expectation of x0 given xt. And that you can just use supervised learning to train for that. So all you need to do is you need to use supervised learning to learn the conditional expectation of x0 given xt, and then you can use Tweedy's formula to turn it into a score, and then you can use the score to sample. And the latter can be learned in a supervised fashion. The question is like, what can go wrong? So like, okay, someone came up with this framework, it looks very nice. So what can go wrong? The thing that can go wrong is that actually learning is not perfect. So we actually do not get to perfectly learn the conditional expectation of x0 given xt. We just write down a supervised loss. We hope that if we have infinite compute and infinite data, we can like learn this perfectly. But at the end of the day, we are not learning this perfectly. And this will actually lead to some problems. And these problems, they do not have to appear in like high dimensional data sets. Even in like very, very simple cases, this actually does fail in a way. So here's the density that we want to like learn. And then we can just use like diffusion models to sample from this like density. And you can see on the right, what is the density that we are actually sampling from. And you can see that like it did like a reasonable job, though there are a lot of errors. And this is like just an 1D example, right? It's not like, I'm not talking about high dimensional distributions, like high resolution phase. I'm just talking about like an 1-dimensional example that seems pretty easy. Diffusion models will actually fail. Like not exactly fail, but you know, the density, there is some error there. And same thing with like 2D examples. This is called the Swiss roll data density. We're trying to like this, like illustrating like a heat map of this distribution. And you see, you know, that you don't match perfectly. And then another one with this little like dots in a circle. The density that you learn is different compared to the one that you wanted to learn. So there is a shift between the training and the sampling distribution. And because we are like fancy people, we will be calling this shift the sampling drift. So let's introduce some terminology. There is this sampling drift that is happening. And like we have already established that the reason this sampling drift occurs is because we did not perfectly learn the score. There are some errors. We could not perfectly learn the conditional expectation, and thus we could not perfectly learn the score. And because of these errors, we have this sampling drift. But if you dive a little bit into the issue, it actually gets a little bit worse. And here's why. There is some error propagation happening because you were at some noisy iterate, right? And you had like, you wanted the score to move, but you had some error in the score and you didn't like move to the correct distribution. So now you shifted a little bit. And you are at an iterate that's coming from a different distribution, and you're gonna ask again your model, what do you think for this iterate? But because this iterate is coming from a different distribution, it was not encountered during training. So you are like, you have two issues. One issue is that you don't learn the score perfectly for the training points. And the other one is because of the recursive nature of the generation process, you're moving to a different distribution and errors accumulate. So during sampling the model, you use it to evaluate it on drifted data, the ones that are coming from the wrong distribution, and you do that recursively. And those points were never like used during the training. And this is actually not specific to diffusion models. Any like recursive generation process has the same issue. For example, LLMs, you know, they're autoregressive models. They generate the word one at a time. And if you have some errors and you're not like sampling from the right distribution, you're gonna be evaluating your LLM in like in points that were not like in the training distribution. And for this point, the score estimation is even worse. First, because we don't have good score estimation to start with, and second, because you're evaluating not the distribution points. So things can go really bad and errors accumulate. And the question is like, can we actually train the model to perform well on these drifted points? Because at the end of the day, this is how we're gonna use the model at sampling time. And this is not trivial at all, because for the non-drifted points, you knew where you needed to go. You started from a clean image x0, you added noise. And you had the model, you're like, oh, this is your noisy iterate, you need to go to the x0. But once you drifted, you don't know how you arrived there. You know, you arrived there because you made some past predictions that were wrong, but you don't know where you were supposed to go. For these points, like, you don't really know what to do. So we're gonna sidestep this issue by enforcing some invariant property that needs to hold no matter what the points are, and no matter where this is coming from, where they're coming from. So let's try to explain what this means. So we have the following thing. We're going to define that a denoiser is consistent. This is our definition of consistency, super important. So we are going to define that a denoiser is consistent if it satisfies the simple property. It has to agree with itself. So what does that mean? Let's see with a visual. So like, let's see what this means. Like on the very left, on the very right, actually, we're in the noisy images. Like for t that is like high, we're in the noisy images. For t that's like low on the left part of the plot, we are like in clean images. T0 is like super clean images coming from the right distribution. There is some time t, and we ask the model, at this point we are next t, and we ask the model, what do you think the clean image is? And the model tells us the magenta arrow, and it says, oh, I believe the clean image is this conditional expectation of x0 given my current prediction. Like that's the magenta arrow. The model believes when you are at time t that you need to go to this blue point, which is the end of the magenta arrow. Okay, we keep that in mind, and then what we do is we run the stochastic sampler. So we sample with the model until a time t prime. We haven't arrived yet to the clean images. And then because the sampler is stochastic, we get a bunch of different points. We get the green point, the brown point, the yellow point. So these are like different points because there's stochasticity in the sampler. And for each one of them, we ask the model again, oh, where do you think I will arrive if I continue this denoising? And you get different predictions. You have the green prediction, the brown one, and the yellow one. And what we are saying is that the denoiser is consistent if the average of these predictions agrees with your prediction initially. So on average, you should be staying consistent with yourself. You should not be changing opinions on average. There's some sort of like martingale property happening here. On average, your predictions should stay the same. And it's actually not that hard to figure out this proposition that says that the optimal denoiser, so what's the denoiser that we want to learn? We might fail to learn it, but what we hope to learn is we hope to learn the conditional expectation of x0 given xt. And this is a consistent denoiser. If you just plug this here, you're going to see by the tile law of expectation that this holds. So the denoiser that we care about is a consistent denoiser, but we might not be able to find it. But you know, there's this consistency property that might be satisfied even though we haven't figured out what the optimal denoiser is. So what we are proposing to turn this into a loss. So while we are training our diffusion models, we're going to have two terms. The first term is the regular supervised learning term, which is basically saying there is some noisy iter at xt. You ask the model, what do you think the clean image is? And we already know that it came from x0. These are the known drifty data points. It's like x0 and xt are coming, but just taking a clean image from the data set and adding noise. We create xt, we ask the model, what do you think x0 is? But then we also want to see how the model performs on the drifted points that are coming from the recursive nature of the sampler. And for the drifted points, we enforce the consistency property. So we are basically saying that the model should agree with itself on average. So if you move from xt to some other points xt prime, you do it many times. For each one of them, you ask the model, oh, what do you think the clean image is? You ask 1 time, 2 times, 3 times. You average all these predictions. The predictions should be the same as the prediction to the point that you started with, which is the point xt. That's and that's a clever. Yes.
Yeah, sorry to interrupt you again.
No,
but like this probably like adds like a lot of cost, right, to your loss. Because like now you have to like for the same point you're going to have to like have multiple predictions.
Yeah, the good thing about this is that you can enforce it locally. So instead of running the sampler for many steps, you can enforce it to local intervals, run it to one step at its point. And if you are consistent in every local interval, you're consistent globally. So the way we actually implement it in practice is that we're not going to run like 20 million points of the sampler and like get different xt primes. We're just going to run like one step of the sampler, but we're going to do it in all the global interval. We're going to partition into smaller intervals, and we're going to apply this locally to each one of the smaller intervals.
Oh, okay, nice.
Yes, and if you want to be even fancier, you can find like, instead of like sampling many xt primes, even for this local interval, there is a way to get an unbiased estimator of this quantity by just taking 2. So we have this derivation in the paper. You know, even in practice, you know, if you get 4 or 5, that's still fine. You know, maybe your training cost becomes like 3-4 times higher, but it's also converging faster. That's what we saw in the experiments.
Very cool.
Okay, cool stuff. So we have some theoretical results about this. I don't want to delve too much in the details, but just to give you a high-level overview of like, if you want to do some theory in this area, what you can hope to prove. One thing that you can prove is that you can hope to prove is that if your denoiser is consistent, then the denoiser is the conditional expectation of some distribution. Maybe it's not the right distribution, not the distribution that you want to sample from, but it is the conditional expectation of some distribution. You can prove that consistency and being the conditional expectation of something, they're like equivalent things. And the second thing is, which is the most important, I think, is that if you have learned the conditional expectation of the true distribution perfectly for some time t, and maybe in some subset of the space, maybe on the non-drifted points. So if you have learned this perfectly there, and you satisfy consistency everywhere else, then you have learned the conditional expectation perfectly everywhere. So that means that if you only manage to learn the conditional expectation on the non-drifted data points, and then for the drifted data points, you satisfy consistency, that means that for the drifted data points, you have also learned the conditional expectation perfectly. So that gives you a way to kind of leverage the drifted data points to learn the score in areas that you wouldn't normally go during training. And like some visual results, you know, if you just generate a bunch of images without consistency regularization, sometimes you get artifacts. Here I'm cherry picking. I'm sorry about that. So I cherry picked some images in which like artifacts appear. You know, here like the cat has like some weird eyes, like the neck on the second picture, we don't know where exactly it is. Also in the third picture, there are weird things happening. If you just take this model and you fine tune like 500 steps with consistency, these artifacts go away for the most part. You know, still there are some issues, but there are like, you see that like just applying the consistency, it's actually visually fixing like problems that might appear. And it leads to state-of-the-art performance. This is why you get published at the end of the day. You just put this table, you're like, oh, I did state-of-the-art, then you get published. So yeah, math is nice, but at the end of the day, what you need to show. So for like classic data sets like AFHQ and CFR10, this leads to improved performance. The improvement is actually not that like important at the end of the day. Maybe you push like 1% the state-of-the-art, but you know, maybe that's what it matters. And if you actually go and check how this property is satisfied, you can actually see that the baseline violates this property more. So that's for the consistent diffusion models. Any questions before I move on to the last part of the talk? Very good. Make sense? Everything clear? Okay, excellent. So moving on to the last part of the talk. This is a topic that I'm getting extremely interested in. So please follow if you can, and like if you have suggestions for collaborations that you want to do on this, I'm very, very interested in that. I'm spending a lot of my time thinking about this problem. And it is the problem of learning from corrupted data. So what does that mean? Let me talk a little bit about what that means. So for certain things, for certain like distributions, we do not ever get to observe clean data samples. For example, as I said, you never get to see an image of a black hole, right? Or you'd never get to see a perfect MRI scan because it depends, like the quality of the MRI scan is proportional to how much time you spend on the scanner. So the more time you spend on the scanner, the better the MRI scan is, but that's like causing like patient discomfort. So you never get to observe like clean MRI scans, but you might be interested in learning how the distribution of the clean things look like without ever seeing a clean sample. And the question is like, are there cases that this is actually like possible, theoretically possible? And let me try to start with a very, very simple example that when I saw it blew my mind. Like, I mean, it was kind of obvious in retrospect, but it was actually interesting to see this. And I think this is something that you can follow as a standalone thing. So, you know, there is some difficult distribution P of X, like it has some density P of X, and we do not get to observe samples from it. But there are some samples X coming from the distribution. We don't get to see them. What we do get to see is we get to see Y, which is this clean sample X plus noise. And maybe we're in the regime where we do have a lot of Gaussian noise. So what is our data set? Our data set is basically a data set of like noisy Alex, noisy Dimitris, and noisy all professors. So we don't ever get to see like a clean image of a professor, but we do see a lot of like noisy images. And the question is like, if I do get to see like a very, very noisy image of Dimitris, can I reconstruct Dimitris? And the answer is like, you're gonna do something, but you're gonna have some reconstruction error. And the reconstruction error depends on the difficulty of the distribution and how much noise you have. So if your distribution is like a Dirac, yes, you can do a pretty good job on that. But like, if your distribution is hard and you have a lot of noise, you know, there is like the signal to noise ratio is gonna bottleneck your performance at some point. So your best guess is going to be the conditional expectation of x given y, and this can be a pretty bad guess. But there's a different question that is like much more important, which is, can you learn the distribution perfectly? Maybe you cannot reconstruct any individual sample, but maybe you learn the distribution perfectly. And is that possible? And the answer is yes for this simple case. And let me convince you why is that true in this simple example. So what happens when you get two random variables and you add them? What happens to their densities? Like back to the probabilities under a course that we all took, what happens to the density when you get two random variables and you add them is that the densities get convolved. So the density of y is basically the convolution of the density of x with the Gaussian density, because like the random variable of y is basically obtained by taking an x and then adding Gaussian noise to it. So the density is getting convolved. But given infinite samples from the y distribution, you can assume that if you have infinite samples, infinite compute and everything, you can perfectly learn P of y. And then you can just deconvolve and get P of x. And how you do the deconvolution, you just go to Fourier space. So you take the Fourier of P of y that you have like perfectly learned, and this becomes the Fourier of x times the Fourier of the Gaussian that you know. And then you solve for the Fourier of P of x, and then you take the inverse Fourier. So that's like a very like simple toy example in which it seems like crazy that even though we cannot reconstruct any individual sample because we have so much noise, we can reconstruct the distribution, which is pretty interesting. Yes.
But we know the noise distribution.
Yes. Like someone, in nature told you that what I did as a devilish adversary is that I add a lot of noise, and I told you that the noise is not adversarial. If the noise is adversarial, you cannot do anything in certain cases. But like if the noise is natural, like let's say it's Gaussian, then it is possible to do this. But you cannot reconstruct individual samples, which is like the tricky part. So in certain cases, we can perfectly learn the distribution from corrupted observations. This is surprising. At least it was surprising to me when I first saw it. And then let's see some examples of what can happen. Like what are some examples of distribution that we might encounter. These are some celebrity faces, but at each one of them there is like a box. Maybe the box has like the dimensions of the box are known, but it's randomly placed in the image. And you get to observe everything that's outside of this box. This is like a potential corruption process. Another one is that you only get to observe the box. So maybe you only get to observe this. So why this would happen? Like an example, aliens visit like Earth, and they want to know how human faces look like. But all of us, we are super afraid that if we give our images to aliens, they're gonna get angry and kill us. So we have an agreement that each one of us are gonna share a part of our face. So that the alien won't know the whole face. Maybe I'm gonna give my eye, the mate's gonna give his smile, and the aliens are gonna see a bunch of parts. And from these parts, the aliens are trying to figure out how the whole face looks like, but they cannot figure out how my face looks like because they only get to see my ear. That's kind of the setup here. And maybe if we are very, very, very careful, because aliens can be very dangerous, we only give random pixels, not even a whole box. We only give random in painting. Believe it or not, you can reconstruct the distribution perfectly from this. And we do train diffusion models to do that. So sometimes we do not have clean data. Sometimes we're afraid of aliens and we do not want to use our data. Sometimes we do not have enough clean data. And sometimes, as I'm going to show you very briefly, learning from corrupted data is actually better, which is another insane fact. So here's the method. It's actually a very simple trick in retrospect, but it's actually a funny one. So normally how you would train this, you would have an image x0, the clean image, you would add noise to it, you would go to xt, and then you would train the model to go from xt to x0. Classic, we all learned that, great. If you learned one thing from this talk, is this is how you train generative models, diffusion generative models. But we can't do this anymore. Why we can't do this anymore? It's because we do not have x0. We only have ax0, where A is an in-painting matrix, let's say, that hides some pixels. And because we do not have x0, we also do not have xt. So one thing we could do is we could say, okay, what do we have? We have ax0, and then we can create A of xt. Maybe A gives us some pixels, doesn't give us some other pixels. So what we can do is for the pixels that we observe, we add a lot of noise. We create A of xt. The pixels that we do not observe, we keep them 0 or whatever. And then we ask the model to go from axt to to A x0, and we can only penalize in the things that we observe. So we have this extra A here. We are saying to the model, oh, your predictions matter only in the pixels you observe. For the other ones, we cannot penalize you. We don't know what's happening. Now, what can go wrong with this? The thing is that, like, the thing that can go wrong is that the model can learn to cheat. Basically, the model knows that in certain locations it's not going to be penalized. So what it's going to do is it's going to, like, perform very well in the location that it's known that's going to be penalized in the pixel that we observe. But for the rest of the pixels, the model is going to do like something completely crazy, and it's going to get 0 penalty in the loss. So maybe there is some inductive bias, and this does not happen that much. But maybe if your corruption is really high, your model doesn't have any incentive to perform well on the pixels that are not observed. In the, like, if you want to put it formally, in the directions that belong to the null space of A, there is no penalty. So for this direction, the model can be arbitrarily bad. So how can we protect from this? This idea is actually like a little bit funny. And it is a little bit funny because we protect by corrupting further. Like we have already corrupted data, and we're going to corrupt further. So this is our AXT, let's say, or AX0 for that case, because we don't have noise. That's a typo. So, you know, you only get to observe some pixels. And what you're going to do is you're going to create a hat of X0 that is basically these green pixels are going to be extra corrupted. We had them, but we went and masked them. Or like only a fraction of these pixels that we observe, we get to mask more. But the critical thing is that, like, in our loss function, we're not going to tell the model which pixels were missing from the beginning and which pixels we had, but we are corrupted extra. And because, you know, if you're giving an exam and I tell you that there are 10 questions, and for these 5 questions, I don't know the answer, and you're only going to be grading these 5 questions, for the ones that I don't know the answer, you can just say bullshit, and I won't have any way to check. But if I tell you, you know, that I don't know the answers to 6 questions, but I won't tell you which one of them, the only way to perform well is to study everything. And that's kind of the idea here that we are doing. We're basically telling you, oh, we don't know the answer, that's true, but you don't know what we don't know. And because you don't know what we don't know, your only bet is you perform well everywhere. And, you know, if, you know, the corruption is like a box, what we're going to do, we're going to have 2 boxes. So we're giving you 2 boxes. You don't know which box was missing from the beginning, which box we corrupted extra. So if you want to perform well on the task that I'm penalizing you, you have to perform well in both boxes, because in one of them, you're going to be penalized and you don't know which one it is. So this is like a new loss. Basically looks kind of the same as the one that we had before. But instead of putting A of XT, we have a hat of XT, which is a little bit more corrupted version of XT. And you don't have to actually corrupt a lot more. Even if I tell you that 1% of the pixel I'm going to extra corrupt, then you are still, if you want to be the best student, if you want to minimize this loss, your best case is to perform well everywhere. Because there are some pixels that you're going to penalize and you don't know which one of them there are. So what's the goal now? The goal is you take as in, like the model takes as input a hat of XT and a hat. You're trying to learn the conditional expression of X0 given what you observe. And that is the minimizer of this function. And obviously, like a trivial way to do this is to make a hat the 0 matrix. But then this is not useful at all because we corrupted so much that the model can only predict the mean of the distribution. We want to keep a hat close as possible to A. That's our goal. Like the best thing that we could learn is a conditional expression of X0 given A XT. But this was not possible with the loss that we had because the model would just like say bullshit to the things that we did not observe. So we are introducing some extra corruption, and we can guarantee that this is actually gonna work. Now there is a generalization of this result that holds for any linear inverse problem, not just in painting, which is there is a way basically to treat other inverse problems as an in-painting problem in some other space. So like as long as some like technical condition is satisfied on the corruption process, you can guarantee that this loss is going to work. And there are ways to do this. The box corruption already showed you how, but there are other ways to do this for general problems, and there is a method to formally get all of these algorithms. So that's kind of how this is. Some experimental results. The first result that we have, which is pretty interesting, is in memorization. So we took like Celeb A, like a normal data, like a very famous data set with like celebrity images. But instead of taking the whole data set, we just took like 300 samples and we tried to train a generative model on them. These are the training images. We have 300 of them. And then we generate some samples and we look at the nearest neighbor of the samples to the data set. And what you see that the model has memorized the data set. The model like literally had only 300 samples, so it perfectly learned all of them. So the generation are basically data set images. This is not helpful at all. Now, if you go and you take this data set and you corrupt it, you corrupt it as a design choice, and then you train it again, you get some new generated samples, but they're further away from the data set samples. So like this was a particular example of a case in which we chose to corrupt. Like we were like kind of crazy, and even though we had clean images, because we only had just a little bit of them, we just decided to corrupt them to avoid memorization. And you can visually see like the similarity value, the distribution of similarity values of the generated image with the nearest neighbor in the data set. And the red line is basically the baseline when you don't have corruption probability. And as you can see, there's like this tail on the right, it means that like the things that have similarity value close to 1, it means that they're identical copies of the data set. But by adding some corruption, like maybe we deleted 80% of the pixels at random, these moved to the left. What you lose is performance, but you can trade performance for memorization. So obviously, if you corrupt a lot, you don't learn as much of the distribution, but at least what you learned is like something new. It's not that like you have learned to memorize the samples. And you can do this at many levels. You can change the corruption probability from 0 all the way up to 0.8. And every time you do this, you should be clicking on the right tail here. What is happening is that like you move a little bit to the left, meaning that you memorize less and less, but there is some cost in performance. And this cost in performance you can perfectly like characterize. So like for certain data sets, we just use different corruption probabilities during training, and we show how like the FID is a metric for performance, lower is better. And obviously the models that are trained on like clean images, no corruption, they perform better. And the FID becomes higher, meaning worse, as you corrupt more and more, but you memorize less. So there is a trade-off between reduced memorization and performance. And this is like particularly useful in applications where you don't get to observe clean data, or you choose to do this. Like here's like I'm showing you different like unconditional generation. On the left there is the training, so on the right there are generations. And you can see how things are changing as I'm corrupting more and more the data set. Even like with very, very high corruption, like this is the training data set. The model never saw like a clean image, but it managed to get a reasonable sense of how the human faces look like. This is like a thing for 90% corruption probability. Cool.
So good question. Would you argue that this like allows you to do faster training somehow when you're using like less pixels or something for the image?
I'm claiming that it allows you to train a general model with limited data that is not memorizing the training set. Like if you train only with 30 images, your diffusion model will just generate all the time these 30 images. But that's a useless diffusion model because you just get back the trainings. If you apply our trick with 30 images, you will get a pretty bad generative model, but at least all of the images are going to be new.
Can you apply it to like text as well, like this idea?
Yeah, we have been thinking about it. We haven't figured out the right way to do this. But this ambient LLM extension, we have been thinking about. And the consistent LLM still is like these problems are related actually. LLMs have the same issues, but yeah, we have been working mostly on the diffusion side. Okay, the last thing I'm gonna show you something actually completely absurd in the last 2 minutes of my talk, and I'm gonna wrap up and take your questions after that. So we actually wanna do something funky. We train a model on in-painting data with our ambient diffusion training, this method that I showed you, the extra corruption. And then we want to use this model that was trained on painted data to solve another inverse problems, like to upscale images. So this is how we trained. And then we want to use this model to upscale images. Now, the crazy thing is like you want to compare how this upscaling performance changes as the number of measurements changes. Like maybe you want to compare how the performance is when you do have like a lot of measurements, and then you want to see how this changes when you don't have a lot of measurements. Okay. And here's the fact, the experimental observation that we figured out, like we observed. We don't know why this is happening, but here's what happens. When you do have a lot of measurements, the model that performs the best is the model that was trained on clean data. So these are like different curves are different models. P equals 0, the blue line is the clean data model. As you change the corruption probability, you train with more and more in painting. So for high measurements, the blue point is the lower in the reconstruction error. So this model was the best for reconstructing images when you had a lot of measurements. The crazy thing that happens is that there is a crossover. So as you reduce the number of measurements, the model that was trained on highly in-painted data performs better than the model that was trained on clean data for super resolution. So that's kind of like crazy because you train on highly painted data and you perform better on like highly downscaled images compared to the model trained on clean data. And this is actually consistent like among different data sets. And it also, if you plot how fast you need to, how many steps of the diffusion process you need to run, the model that is trained on like clean data is actually much slower. So for whatever reason, training with corrupted data gave you a better prior in terms of like speed and performance in the high corruption regime. So okay, a recap, generative models can be very useful priors for inverse problems. Modern generative models are diffusion models, and they work by denoising images iteratively. There is propagation of errors happening because of the recursive nature of the generation process, but this can be corrected with appropriate techniques, like in our consistent diffusion paper. And we can train generative models even without having access to clean data, which is very useful in certain applications. And the most crazy thing is that like models trained on corrupted data can actually reduce memorization, but can also lead to improved inverse problems performance compared to models trained on clean data. And that's all. I'm ready to take your questions, and thanks so much again for having me.
One simple question. So in your crop image data set, so do all the images have the same corruption? So for example, like if all the images they are cropped, like just have one that's missing, then even if you crop it more, well, would this training algorithm make the diffusion model think image with an empty box is the best image? Why would it also fill other boxes?
Because you create two boxes
that
are not overlapping. You know, maybe if your box is really like higher than like half of the image, then you cannot do this. But if you create two boxes that are not overlapping, one of the boxes was the one that was missing from the beginning, and the other was the box that you corrupted. And if I show you the two boxes missing, you don't know which one is which. Like you cannot tell me like, oh, like this is the one that was missing from the beginning, this one that you corrupted. There are two boxes missing. You don't know which one it is. And what I'm gonna tell you is I'm gonna tell you that you're gonna be penalized on one of these boxes. And because you don't know which box it is, what are you gonna do? You're gonna hope to do the best in both of the boxes, and then see at which one you get the penalty at the end. Yes.
So your ambient diffusion model.
Yeah.
Okay. So can that be theoretically related to some compressive sensing literature or something?
Yes. So there are a lot of theoretical questions coming into play here. One of them is like, when can you learn? Like information theoretically, when can you learn? And as you very well understood in the beginning, like that has your corruption process has to be natural. Like if your noise is adversarial, you cannot learn. Like in the compressed sensing, there is an information theoretical result that tells you that you can learn from compressed sensing measurements. I think it's called Kramer-Waltz theorem. It's actually kind of, if you spend some time figuring out the details, it's not that hard to figure it out that this can happen. The other questions that are really open is like how many samples you need to actually learn. Like because most of these results that at least we have and from prior work, they are holding in the case like that you have infinite samples, like the example that I showed you with the Fourier and the deconvolution. Like a very interesting theoretical result for compressed sensing is how many do you need in order to learn reasonably well the distribution. And then the other question is how you create a hat given A, and for different corruption process, there are different ways to create. For compressed sensing, for example, what you observe is you observe M linear measurements, Gaussian measurements from A. What you're gonna do is you're gonna delete one of them. So A hat is gonna be M-1 linear measurements. And because it's an undefined system, you still can't figure out which one is missing, and you're still gonna be learning the correct thing. So yes, the short answer is it's a great question. There's a lot of research to be done, and many of the things are very open right now.
Yeah. So, and maybe I missed this, but did you train also on the MRI images for your case, or were you showing it from a different?
So for the MRI case, we did not train on corrupted images. There was a different paper that I saw in the beginning. There is a follow-up work from friends, DUT, they're doing MRI. that they are like training MRI with noisy data. So like all of their MRI scans are noisy, and they managed to use a variation of this algorithm that actually works, and they can generate like clean MRIs.
So in that sense, they did corruption, like your algorithms are just on top of an existing noisy image or not?
Yeah, like you can like the one that I saw this for linear measurements, like AX. They have some algorithm that works on noisy also, and you can combine these two and do noisy and linear, which is the full model. But they have applied this to MRI for the noisy case. For the linear, like Y equals AX, I don't think they like anyone has applied this to MRI yet. But I think I know a lot of people that are like thinking about or working on it.
Giannis?
Yes.
So like in the ambient diffusion case, like you have two corruptions, right? One that you introduced and one that came naturally.
Exactly.
Do those two corruptions have to be like similar in some sense, or can they be arbitrarily different?
They can be like, you need to be fooling the model. You need to make sure that like someone that's so like you like if you show me an image, I need to be confused about what was missing from nature and what was missing from you. And the missing is just like a very vague word on purpose. But yeah, the short answer is that like for the case that I'm aware of, at least, it makes sense to keep your corruption process close to the natural corruption, because then it's easier to fool the model about like which thing was actually missing and which thing you introduced, like you further.
Got it. If it's too different, then the model will figure out which one are the ones you did, and it will say, okay, I need to care about these, I don't need to care about the others.
Yeah, for example, if there is a missing box from nature and then I introduce random in painting, the model will figure out, this missing box is actually missing, you don't have it, because you always don't penalize me there. So
got it.
It's not gonna, there is some theoretical condition that I briefly showed for the sake of like saving some time, that makes this like formal of like what conditions your A hat should satisfy, but it depends on the case of how exactly you design A hat.
So in some sense, I need to be able to know how to reproduce nature's corruptions.
Right. You definitely need to know how nature corrupted the images, and you also need to be a little bit clever about how you create a hat.
Oh, okay, cool.
Any other questions?
There's no question. Thank Giannis again.
Thanks so much. Awesome. Thanks so much again. I'm gonna stop sharing. Thanks everyone that joined through the Zoom meeting as well. See you all.
Hopefully see you soon, man. Thanks for the great talk.
Bye.